Hello. In this video, we will cover section 5.2, which is on theoretical probability. Probability are always numbers between 0 and 1, including 0 and 1. Probabilities are measured as fractions, decimals, or percentages, such as 1/2, 0.5, or 50%. If an event never happens, then the probability is 0. If an event always occurs, then the probability is 1. The probability an event not happening is 1 minus the probability that the event will happen. This is called the complement of the event. For example, the probability of rolling a 1 on a dice is 1 in 6, 1/6. The probability of not rolling a 1 is 1 minus 1/6, which equals 5/6. And that's the same as the probability of rolling a 2, 3, 4, 5, or 6. Again, the opposite of rolling a 1. Events are typically described with uppercase letters, such as A, B, or C. Example, let A represent the event, it rains tomorrow. Then P of A, written in that format, P parenthesis, capital A, then N parenthesis, means the probability it rains tomorrow. And then if we were to write if P of A equals 0.5, then we would translate that as the probability it rains tomorrow is 50%. Putting this together with the definitions on the previous page, we can say that given event A, rule 1, the first rule, which is the range of possible outcomes, the probability is going to be between 0 and 1, including 0 and 1. Rule 2, which is the complement rule, the probability A does not occur equals 1 minus the probability that A does occur. Or you can go through and you can use this uppercase C here to represent the complement, and then this says the same thing in symbols. The sample space is the list of all possible outcomes of an event. So for example, the flipping a coin sample space would be heads or tails. H and T represent heads and tails respectively. The dice sample space would be 1, 2, 3, 4, 5, and 6, which is the number of pips that would show up on top of on a dice if you were to roll a dice. And then a deck of cards sample space would be the 2 of hearts, the 3 of hearts, all the way through the ace of hearts, then the 2 of diamonds, the 3 of diamonds, all the way through the king of diamonds, and so on. Or sorry, and the ace of diamonds. The event space is the list of all possible outcomes from the sample space that define an event. So for example, if the event were flipping a coin and getting heads, then the event space would be just H, right? If the event were rolling a dice and getting odds, then the event space for that, then the event space would be 1, 3, or 5. And then if the event space were drawing an ace from a deck of cards, then the event space would be the ace of hearts, the ace of diamonds, the ace of clubs, and the ace of spades. Okay, so the sample space is all the possible outcomes of an event, and then the event space is the list of that is the outcomes from the actual event that satisfy the event. Assuming outcomes are equally likely, we can calculate the probability of an event by comparing the number of outcomes in the sample space with the number of outcomes in the event space. Okay, so we can go through and make a ratio where the probability is going to be the number of outcomes in the event space divided by the number of outcomes in the sample space. So for example, suppose there are 30 people in a class. A person at random is selected to win a prize. What's the probability that any individual wins the prize? Well, you have the number of people who win the prize over the number of people in the class. So we just create ratios. That's how we do probabilities. All right, so let's look at another example. Suppose a bowl contains 5 red dice, 3 green dice, and 2 white dice. What is the probability of drawing a red dice, a green dice, or a white dice? Well, the probability of the red dice would be the number of red dice over the total number of dice. So there's 5 red dice over 10 dice total. And then the probability of a green dice would be the number of green dice, which is 3, over the total number of dice, which is 10. And the probability of a white dice would be the number of white dice over the total number of dice. All right, let's look at another example. So let's say you roll 2 dice and you add the outcomes. What is the probability that the sum would be a 7? Okay, so this is what not to do. So if you think about it, there are 11 possible outcomes for rolling 2 dice and adding the outcomes. The smallest would be 2. That would be if you roll the 2 dice and you got a single pip on each dice. And then the highest would be 12, which would be you roll a dice and you get 6 pips on each dice and you add it up and you get 12. And so if you were to list the possible outcomes, 2 to 12, and say, okay, that's my sample space, I'm going to roll, and then there's one of those has a 7, so you can't see it in there because I didn't write the entire list, but one of those 11 would be the probability. So why is that what not to do? That's not correct. Well, the reason is that the outcomes are not equally likely. There's only one way to roll a 2, while there are 6 ways to roll a 7. So those 6 ways would be you have 1 pip on one dice and you have 6 on the other, 2 and 5, 3 and 4, okay, and then so on. Okay, so since you're rolling 2 dice, you could reverse those as well. So the first dice gets a 1 and the second dice gets a 6 versus the first dice gets a 6 and the second dice gets a 1. Those are counted as 2 separate events. So what do you need to do? You actually need to write out the full sample space and then identify the outcomes that would sum to 7. So the full sample space is you could get a 1 pip on one dice and 1 pip on the other, 1 pip and 2, 1 pip and 3, and 1 pip and 4, and so on. Okay, and then this goes all the way to, and the order does matter here. So you're getting 1 pip on the first dice, 1 pip on the second. Or sorry, maybe it's better here. So you get 1 pip on the first dice, 2 pips on the second is different from 2 pips on the first and 1 pip on the second. Okay, so if you write out the full sample space with 2 dice, there are going to be 36 possibilities. And so that's your size of your event, that's the size of your sample space. And then your event space, you'd have to look in the full sample space and identify all of the outcomes that end up with a 7. So we'd get 1 and 6, that sums to 7, 2 and 5 sums to 7, 5 and 2 sums to 7, 6 and 1 sums to 7. So there are 6 total. And so if you then go through and do the probability, it's the number it's again still the ratio here, number that summed to 7, which is 6, over the number of total results, which is 36. So the thing that you've got to watch out for, the difference between these is whether the outcomes are equally likely, right? So all of these outcomes are equally likely when you roll 2 dice, whereas if you just write out the possible outcomes, these are not equally likely. 2 and 12 are equally likely, 3 and 11 are equally likely, but 2 is not equally likely with 3. There's one way to get a sum of 2 from 2 dice, where there are 2 ways to get 3. Okay, let's look at a homework example now. A study found that highly experienced teachers may be associated with higher student achievement. Suppose students are randomly assigned to one of 8 teachers, and then it gives a list of names there. It says some of those are highly experienced and some of those are less experienced. All right, so the first thing it asks us to do is to list the possible outcomes when a student is assigned to a teacher. And then when we're done doing that, it wants us to list the probability that a student is assigned to a highly experienced teacher. And then when we're done with that, it wants us to list the complement of the event in B and what is the probability. All right, so first, the list of all possible outcomes when a student is assigned to a teacher, that's going to be the list of all the teachers, right? So we've got the student could get Perry, Tran, I'm not going to pronounce all these names because I'll probably mispronounce some of them. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So there should be 8 things that are in our sample space. And then what is the probability that the student is assigned to a highly experienced teacher? So we're going to have 1, 2, 3, 4, 5, 6 highly experienced teachers over the total number of 8 that I just said from the previous one. And then what is the complement of being assigned to a highly experienced teacher? So it's the opposite. You could think of it as the opposite. So the opposite of being assigned to a highly experienced teacher is going to be assigned to a less experienced teacher. And then the probability of that would be 1, 2 out of 8. So let's just take a look. I typed all that up. So list the possible outcomes. So we've got the 8 teacher names. What's the probability the student is assigned to a highly experienced teacher? So that's the number of highly experienced teachers over the total number of teachers. And that's going to be 75%. What event is the complement of B? All right. The complement is going to be the complement of being assigned to a highly experienced teacher is being assigned to a less experienced, and the probability of the less experienced teacher. There's 2 less experienced teachers out of 8 teachers total. And so that's going to be 25%. Let's look at another homework example. In a standard deck of playing cards, there are 4 suits: clubs, diamonds, hearts, and spades. Following cards appear in each suit: ace through king. Jack, queen, and king are called face cards. Diamonds and hearts are red, and clubs and spades are black. If you draw 1 card randomly from a standard 52 card playing deck, what's the probability of each of the following? So what's the probability of getting a 10? What's the probability of getting a red card? What's the probability of getting a club? What's the probability of getting a non-face card that does not have a face on it? And then what's the probability of getting a jack or a queen? Okay, so let's just go through the basics of these and then we'll flip over to the actual solutions. So the thing you want to do when you're going through and finding so you want to count up how many things are in the event space versus how many things are total. So we know that there's a total of 52 cards. So each one of these is going to be over 52. And what we want to do is we want to count out of the 52 cards, how many 10s are there? So we've got a 10 for each suit. So there should be 4 10s. How many red cards are there? Well, we know diamonds and hearts are red. So we know that we're going to have 13, and we've got 13. If you count these up, there are 13 of these. There's 13 diamonds and 13 hearts. So we should have 26 total red cards. How many clubs are there? All right, so there's only 1 suit that's counted as clubs. And so we've got 13 of those, an ace of clubs, a 2 of clubs, all the way through a king of clubs. Non-face cards. So how many cards are non-face cards? Well, we know that we've got, we've got 1, 2, 3 face cards, and there are 4 suits. So that means there's going to be a total of 12 face cards. Take 3, multiply by 4. So 12 of the 52 are face cards. That means 40 are non-face cards. And then next we've got a jack or a queen. So how many jacks or queens are there? So we've got a jack for each suit. That's going to be 4 jacks. A queen for each suit. That's going to be 4 queens. And so that means we have a total of 8 jacks or queens out of our 52. So let's take a look at that. 10, we've got 4 out of 52. That's what we said. Red cards, 26 out of 52. Clubs, 13 out of 52. Non-face, 40 out of 52. And jacks or queens, 8 out of 52. All right, let's look at another homework example. The sample space below shows all possible sequences of child gender for a family with 3 children. The table is organized by the number of girls. All right, so this is what this is showing is the possible ways in which you could have children. You could have, if you had children, you could have a boy, and a boy. You could have a girl, then a boy, and a boy, then a girl, then a boy, a girl, girl, boy, girl, 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 girl. That's all the different possible outcomes if you go through and you have 3 kids. So how many outcomes are in the sample space? Find the probability that you get all girls, find the probability of no girls, and then find the probability of exactly 1 girl. Okay, so the number of outcomes in the sample space, how many is that going to be? So what we can do is we can just count them up. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, or 8 possible outcomes in the sample space. So find the probability of all girls. So we want to look and see how many of these have all girls. There's only 1. So we should have 1 out of our 8 is the probability. So there's 1 outcome that has all girls out of 8 total possibilities. Find the probability of no girls. So there's also only 1. 1 out of the 8 has no girls. And then finally, we want to find the probability of exactly 1 girl. All right, well, this doesn't have exactly 1 girl. Nope, those don't. Those have 2 girls. That has 3 girls. Nope, we just want these. These are the only possibilities that have 1 girl. So we've got 1, 2, 3 that's in our event space out of a total of 8. And you can see on the next page, all that written out. How many outcomes? 8. Find the probability, all girls, the number of all girls over the number of possibilities. And again, I did the same thing with the probability. I think I cut and pasted, that's why. And then that's, again, 1 out of 8. And then there are 3 cases with 1 girl out of 8 total. More complex events can be created by using and or to combine events. The probability of A and B is the probability of satisfying the criteria in both event A and event B. The probability of A or B is the probability of satisfying the criteria in either event A or event B or both. So let's look at an example. Find the probability that a person is wearing a hat, wearing glasses, wearing a hat and glasses, and wearing a hat or glasses. So the idea is to look at the picture. It's a little bit small. So it may be difficult to see, but it wants us to go through and figure out the probability. So again, the probability is still going to be the same as what we talked up to this point. We're going to have the number of outcomes that are satisfied, the number in the event space over the number in the sample space. Okay, so wearing a hat, if we look closely at the picture, I think the next page just has the answers. Yeah, let's just look, let's try and do this without flipping over. So we've got hats, we've got that person has a hat, that person has a hat, that person has a hat. So it looks like we've got 3 out of the 8 have hats. How about glasses? That one's really hard to tell. I think this person has glasses, this person has glasses, this person has glasses, and maybe that person has glasses. So maybe there's 4 out of 8. We'll find out the correct answer on the next page. I should have made this image bigger. All right, and then wearing a hat and glasses. All right, how many people are wearing a hat and glasses? We've got 1 person. Maybe that's a second person if that person has glasses on. And then wearing a hat or glasses. So all you got to do is just be doing one of the 2, and that gets you in the list. All right, so this person has glasses on, so that they count. This person has a hat on, so they count. Hat and glasses, that's okay. Both still counts. Glasses, that one counts. And that we definitely have a hat there, and so that counts. All right, and so with the and, you just want it, they have to be both, all right, to meet the criteria. And or they only have to just meet one of the criteria to be in the event space. All right, so let's take a look and see what we actually got. So we can compare to the picture here again. I think the reason I did the picture small was so that it would fit on this page. All right, so the number wearing a hat, we said that's 1, 2, 3. Okay, that was correct. And there are 6 people total, so 6 people in the sample space. 3 have a hat out of 6 total. That reduces to 1/2. How many wearing glasses? All right, so we said, I guess that was 1, 2, 3, and I guess that person was wearing glasses, so it's hard to tell. And that looks like that was correct. 4 out of 6, which reduces to 2 out of 3. Hat and glasses. So hat and glasses, we said 1 and maybe 2 if this guy had glasses on, and he does. So that's 2 out of 6, which is 1/3. And then hat or glasses, we've got 1, 2, 3, 4, 5, 5 out of 6, and that was correct. All right, let's look at another example. So find the probability that a person is married, has college or higher education, is married and has college or higher education, and is married or has college or higher education. Okay, so we want to go through and look through our table here to do that. So to find the probability that a person is married, so just married. All right, so if we look at just married, so this person, these are married, these are married, these are married. We've got a total of 408 are married out of 665 total. Okay, so we would just add up down this column. All right, now next, has college or higher education. So college or, so these people have college or higher, these do, these do, these do. So we have 143 total have college or higher education out of 665 total. Okay, so those are straightforward. Then where it gets new is that we have how many people are married and have college or higher education. So here we have, these are the ones who are married. These are the ones who are college or higher education. And what we want to do is we want to find what, what's contained in both of the, not, well, both is, yes, both. You want to find the intersection of those two. And so that's just going to be this, right? So these people are married, but they do not have college or higher. These people are married, but do not have high school or higher. These people are college or higher, but they're single. The only people that meet the criteria of being married and has college or higher education is this box here, which is 90. So we get 98 out of 665. And then finally, we have married or has college or higher education. So that means, or means we want to count everyone who meets either criteria. So these people are all going to be counted. These people are all going to be counted. So what you can do is you can go through and say this whole row, this whole column, and this whole row, if we add those 408 and 143, all right, then we're going to get close. But the issue that if you do that, if you add the column here and add the row, then you've counted 98 twice, because 98 was in the married column and in the college or higher education column. So you need to subtract off that 98. The other way you can do it is you could go through and you could do this plus this plus this plus this plus this plus this. You could add everything one time, or typically the easier way is just to go through and add down the column, add across the row, and then subtract the overlap where you counted twice. All right, and we can see those results here, 408 out of 665, 143 out of 665, then the 98 out of 665, and then the 408 plus 143 minus the 98 that we double counted, which is what I wrote over here off to the side to explain that. Okay, so let's look at another probability rule. The probability that event A or event B happens is the probability of event A plus the probability of event B minus the probability of event A and B. Okay, so what's happening there is it's writing up a formula for adjusting for the overlap. So one of the observations that you can make from the previous page is you can see how when we did the or, we went through and we ended up taking the and results. Yeah, the and result is 98 over 665, and we ended up subtracting the and result. So this is the probability of event A that they're married. This is the probability of event B that they're college or higher, right? So we got this, and then we went through and we subtracted off the and. And so what this is doing is it's just writing that up as an actual official formula. If you do have that situation, probability of A or B, you can find the probability of A, add the probability of B, and then minus the probability of A and B to go through and remove the overlap, remove the double counting that you did if you went through and added those up. All right, so when two events have no outcomes in common, that is, when it is impossible for both events to happen at once, they are called mutually exclusive events. So for example, from the hat sunglass example, it is impossible for a person to be wearing a hat and not wearing a hat, right? That's a silly example, but that we would say the event a person is wearing a hat and a person is not wearing a hat are mutually exclusive. You can't be both. And then if we go back and look at the relationship education example, it is impossible for a person to be married and be single at the same time. So the events the person is married and the person is single are said to be mutually exclusive. All right, so if we go through and do so we find the probability that a person is married or person is single or is married. All right, so if we find the probability that a person is married, we would just go through and add down the column. That's 408. If we go through and find the probability that person is single, that's 112. All right, and you'll see if you look at those don't overlap. All right, so there's no overlap to end up subtracting. There's no double counting there. And so if we were to find the probability that the person is single or is married, that's going to be 112 plus 408. All right, and we did that on the next page. So if you do that, we get 420. And I went ahead and said, notice that unlike the first time, we did not have to subtract double counted events. That is because there weren't any. When find the probability of or events that are mutually exclusive, there's no double counted events to subtract. And so what we can do is we can create a new rule for A, like a sub event for rule 4, a sub rule for rule 4. And that is that when A and B are mutually exclusive, you don't have to do the subtracting part. And that's because that if you go through and find the probability of A and B when the events are mutually exclusive, you get 0, right? If A and B are mutually exclusive, if A and B don't have any overlap, then the probability of that happening is going to be 0. There's not going to be anything in the event space if there's no overlap between the two events. All right, and so we do have this sub rule that we can use for when events are mutually exclusive, just makes the or rule a little bit simpler. All right, let's look at an or rule example. So it says go through and roll a 6-sided die, find the probability that you roll an even number or a number greater than 4, and then roll an even number or a 5. Okay, so let's look at the first one here. So since there are even numbers greater than 4, the two events are not mutually exclusive. So we need to use the default rule 4 when it comes to finding this probability. So the probability that we get an even or a number greater than 4 is going to equal the probability that we get an even plus the probability that we get a result greater than 4 minus the probability that we get an even that is greater than 4. So the probability of an even, there's 3 even results when you roll a die, so 3 out of 6. The probability that you get a result greater than 4, so that's this one here, a greater than 4, well, you could get a 5 or you could get a 6. So there's 2 possibilities on when you roll a 6-sided die that would be greater than 4. And then how many evens are there that are greater than 4? Well, 6 is an even and is greater than 4. And so we want to remove that. Otherwise, because we double counted it. It was counted in this result and counted in this result. And so if we remove it, there are 4 different possibilities out of 6 or 2/3 probability that you'd get an even or a greater than 4 when rolling a dice. Okay, and then for the second case, roll an even number or a 5. All right, so since it's not possible to roll an even number and a 5, then the two events are mutually exclusive. So then we can go ahead and use rule 4a there. All right, so probability of an even is 3 out of 6. The probability of a 5 is 1 out of 6, right? So this is obvious, right? So evens and 5 is odd, and so it's not going to be an even number. So that's why the two are mutually exclusive. And so we've got the 3 out of 6 for the even, the 1 out of 6 for the 5, and then we can add those and get our probability. All right, let's go through and look at a chart example. All right, so Pew Research examined the top science-related Facebook pages to determine the types of posts that were made. They found the results in the chart. What is the probability that a post from these pages is an advertisement, is not related to science, or falls in the other category? Okay, so these are all mutually exclusive. You cannot be in the discoveries category and in the applications category. Okay, and so because of that, we can go through and just add up the results. So advertisements, we have, looks like 16%, is not related to science, that's 5%, and then other category, that's 10%. So we can find the probability just by adding those up. And what happens when we do so? We get 31%. I think that's the last slide. Oh, nope, there's another homework example. My apologies. All right, so a poll asked respondents to fill in the blank to this question. Compared to other industries, there is blank discrimination against women in the tech industry. Responses are separated by gender are shown in the table. Find the probability that the person is a woman and said more. Find the probability that the person is a woman or said more. Okay, so it wants us to go through and do that. So let's see, find the probability that a person is a woman and said more. So we've got these are the women and said more. Oh, and there we go. So there's the more. It took me a second. I was like, wait, where's the more? It's right there. So a woman who said more, there's going to be 41 of those out of 414. Okay, find the probability that the person is a woman or said more. So we've got, you only need to meet one of the two criteria to be in there. So we've got, here are the women, that's 133. Here are the mores, that's 110. But then we have to adjust for the fact that we've double counted the 41. The 41 is counted in the 133 and in the 110. And so we need to remove that by subtracting that off at the end. All right, so find the probability the person is a woman and said more. Woman and more, we get 41 out of 414. That's 9.9%. And as a woman or said more, we could see we've got the 133, the 110, and then we subtracted off the 41 because we've double counted it, and we get a result. So is that it? Nope, there's one more example. There's another example. All right, so a single 6-sided die is rolled. Find the probability of rolling an odd or a number less than 4. All right, so can you roll an odd number and is less than 4? Yes, these are not mutually exclusive. Okay, so we're going to have to go through and use the rule 4 as originally defined. So let's take a look at that. Find the probability of rolling an odd or, I don't know why I wrote less than 6. It should be less than 4, right? Okay, that's just a typo. All right, so odd or less than 4. So here are the odds. There are 3 odd results out of 6 total when rolling a die. Okay, and then less than 4 would be you could roll 3, a 2, or a 1. So there are 3 possibilities that are less than 4 out of 6 total. And then we need to subtract off those that we've double counted. So how many odd results are there less than 4? Well, 1 is odd and is less than 4, and 3 is odd that is less than 4. And so we've double counted 2 results that we need to subtract off. And if we go through and do the math, we get 3 plus 3 minus 2 is 4 out of over 6, which reduces to 2/3. Okay, and that is it. Thank goodness. Okay, so that's the video. Thank you for watching, and I'll see you next time. Bye-bye.